in this video, we're going to be working some AP Calculus particle motion problems. And these are going to be the type of particle motion problems where the motion is restricted to a straight line, like along the x-axis or the y-axis. A lot of these are going to be free response questions from Calculus AB exams. Some of them will allow a calculator, some will be no calculator, like this one. The first one's like a particle moves along the x-axis so that at time t, its position is t cubed minus 6t squared plus 9t plus 11, and we're wanting to find the velocity of the particle at time t equals 0. Okay, so we're going to first take the derivative to write the velocity, so that'll be 3t squared minus 12t plus 9. And then we're going to plug in t equals 0, and we just get 9. Okay, that one's pretty easy. And then, okay, during what time intervals is the particle moving to the left? Okay, so I'm thinking moving to the left, that's where the velocity is negative. So I need to find where's the velocity negative. I need to either sketch the graph or make a sign chart for this velocity function, but either way, I'm going to need to find the zeros or like factor. So first I'm going to see all three of the numbers on it are divisible by 3, so I'm going to factor out the 3. And see, I'm left with t squared minus 4t plus 3, and then that is t minus 3 times t minus 1. And so the zeros of this would be t equals 1 and t equals 3, so I could sketch a graph of it, something like that. It's an upward-facing parabola. If you want to make a sign chart, it would be the same information. And we would see that the velocity is negative between t equals 1 and t equals 3. And then what is the total distance traveled by the particle from t equals 0 to t equals 2? Well, fortunately, we've got a sketch of the graph of velocity because total distance, that's the thing that we learned about recently, that's going to be the integral from 0 to 2 of the absolute value of velocity. And if we go over here and we see that 2 is halfway between 1 and 3, we've got a sign change and we need to be careful about that. Okay, so I kind of might use some color and say, okay, through here, the velocity is positive, and over here, the velocity is negative, but we don't need those counteracting each other. Okay, if we've got a calculator, this is really easy to do. We just put absolute values around the velocity equation, and the calculator does the work for us. Without a calculator, it is a little bit more annoying. We're going to have to split it up into the integral from 0 to 1. Okay, yeah, it's like the 1 is underneath the one is supposed to be the y-axis. That's 1. Okay, that makes it look a lot better. So it's going to be the integral from 0 to 1 of velocity, which I'm going to go back here, 3t squared minus 12t plus 9. Then I'm going to add the red area. I'm just going to make sure it's positive. I'll put absolute values around it because I know this one's going to come back negative. 1 to 2, same velocity. All right, and I'm going to just kind of zoom in and get to it. Now, you might go and make sure that, you get that. And an option that you have is you can just find the positions and, do the same work because it's all equivalent using the fundamental theorem is what I'm saying. You can just go and use x of t, and you can see that this antiderivative of velocity that I'm going to use to compute the definite integral is related. I'm just not going to worry about the 11 each time. Because the 11 is just it was already accounted for, and we're just looking at the change in position here. So, all right, that's going to be 1 plus 9 is 10, minus 6 is 4, minus 0. Then in red, let's see. Okay, that's going to be 8. 6 times 4 is 24 plus 18. All right, so I've got 26 minus 24 is 2. Minus, if I plug in 1, I got 4 the other time. Okay, so 2 minus 4 is negative 2. Okay, so I need to add the absolute value of all of that. Let's see, so let's put my absolute values around that. Doesn't really look great, but And it ends up being an absolute value of 2 minus 4. And I kind of like that strategy because it's like I knew it needed to be negative, and had I not gotten a negative number there, that would have been cause for concern. I would have kind of had second thoughts there. So 4 plus 2 is going to be 6 units of total distance traveled. Okay, and I'll be honest, I don't love that. And that is a thing that you can be asked to do in AP Calculus, but I will say that's probably not a thing you're going to be asked to do very often, if ever again in my class. Maybe one more time on this homework, but not something I'm interested in doing a whole lot. That's one of the great things that the calculator offers us, is the ability to take the integral of the absolute value of a function without so much analysis. Okay, so this one's another no calculator. A particle initially at rest moves along the x-axis so that the acceleration is 12t squared minus 4, and we've got an initial position. Oh, I kind of read past the initially at rest. We do need to be able to translate that to say that, okay, velocity at 0 is going to be at 0. All right, so find all values of t for which the particle is at rest. Okay, we're going to find the velocity, so that's going to be an antiderivative for 12t squared minus 4 with respect to t. It's looking like add 1 to the power, divide by the new power, minus 4t. Maybe take a second to check your antiderivative. 12t squared minus 4, yeah, that makes sense. Maybe plus a c. But we know that v of 0 equals 0, so I can see that c is going to equal 0. And so if I've got velocity equaling 4t cubed minus 4t, I can factor that. Okay, and if I'm interested in when it's at rest, I could say velocity is 0 when t is equal to 0 from the 4t equaling 0, when t is equal to 1, or when t is equal to negative 1 from the t squared minus 1. Okay. Now, writing an expression for the position, we're going to need to antidifferentiate the velocity. So x is going to equal an antiderivative for 4t to the 3 minus 4t with respect to t, which would be, okay, add 1 to the power, divide by the new power. That's 1t to the 4. Minus 2t to the 2. Pause for a second, check the antiderivative. 4t to the third minus 4t to the first. There will be a plus c. They told me that x of 1 is equal to 3. All right, so 3 is going to equal 1 to the 4th minus 2 times 1 squared plus c. So I think c is going to need to equal 4. So my position function is going to be t to the 4 minus 2t to the 2 plus 4. And then find the total distance traveled by the particle from t equals 0 to t equals 2. Okay, I've got... Okay, this is the exact same story. Maybe I'll do the same. Maybe I'll do it the other way and just say, okay, I've got sign changes in the velocity at 0 and 1. So from 0 to 2, I just need to think about, okay, x of 0 equals, yeah, because I think I know x of 1. Yeah, I like that. All right, so x of 0 is going to be 4. X of 1 equals 3 from the statement of the question. And x of 2 equals 2 to the 4 minus 2 times 4 plus 4. So that's going to be 12. Okay, and if I go from 4 to 3, that's a total distance traveled of 1 backwards, but it's still 1 unit total. Then from going from 3 to 12, that's a total distance traveled of 9, and so this would equal 10. And that's equivalent to what you would get if you set up a bunch of integrals and solved the way I did in blue and red up there. And that's maybe, a different way of thinking about it, and that is equally valid, provided you've, shown the work that led to you getting the position function in the first place, which we certainly did. Okay, so the graph of the velocity of the particle is shown below. The distance traveled is 20. So we know that the integral from 0 to 6 of the absolute value of velocity is 20. And the displacement is 12. So the integral from 0 to 6 of regular velocity is 12. What's the value of the integral from 4 to 6? We know it's going to be negative because it's sitting below the t-axis. But I might go over and like kind of give these areas names. So I might call this area A and this one area B. And, we can say that the areas are going to be positive numbers that represent just the areas of the regions. But we know that the integrals are going to be like positive and negative depending on if we're taking the absolute value of velocity or not. So when I take the integral of the absolute value of velocity, I'm going to be adding the two areas. So that would be like A plus B equaling 20. And if I'm looking at displacement, just the integral of velocity, that area B counts negatively. So A minus B is equal to 12. And this is a 2x2 system, linear system of equations, and it really looks prime for solving by elimination. And we don't do this all that often, but we have done it like at least once before in this class. So we see it's set up for elimination. We're going to add the two equations to each other, and we'll get 2a equals 32. And that's revealing to me that a is equal to 16, which is, not exactly what we're looking for, but it should help because, 16 plus 4 is 20, and 16 minus 4 is 12. Okay, so that means that the area of B is going to be 4, and the integral from 4 to 6 of velocity would be negative 4. Because the area is underneath the t-axis, the velocity is negative, so the object's going to be moving to the left along the x-axis, and so the change in position, the integral from 4 to 6 of velocity, should be negative. All right. Now the figure below shows the velocity. Tablet had other ideas. The velocity is moving on a straight line. The velocity is meters per second. We've got an initial position. Okay, we want to find the position of the object at time t equals 0. All right, so what we can do is we can integrate the velocity between t equals 0 and t equals 4 to find the change of position. That's the fundamental theorem of calculus. So I'm going to say the integral from 0 to 4 of velocity, and that I can also find that using geometry over here on the figure. That's going to equal the antiderivative of velocity, which is position, the net change in that from t equals 0 to t equals 4. So that's going to be x of 4 minus x of 0. And I already, I guess we're calling that s. Pardon me. And we happen to know that s of 4 is equal to 3, so that's going to be 3 minus s of 0. But we can still do work on this integral right here. So the integral from 0 to 4 of velocity is going to be the amount of area in here. So I might, oh wow, this is at 5. Okay, but that's not that bad. All right, I'm just thinking about what I want to do here. Oh. Well, this is not the nicest grid ever. I'm definitely going to cut it up into this triangle because I can see it's got a width of 2 and a height of 10, so it's going to be an area of 10. Then I guess I'm just going to average the bases. Okay, so 10 and 5. Okay, so it'll be 7.5 multiplied by 2. 15. All right, well, 15 is going to equal 3 minus s of 0. And so I believe that would mean that s of 0 was negative 12. Okay, what is the total distance traveled by the object from t equals 4 to t equals 8? Okay, well that just means I'm going to need to do some more area computations. 4 to 8, absolute value of velocity. So I'm just going to count everything positively. That's got a width of 1 and a height of 5. Width of 1, height of 5, and it's a triangle, so that would be 2.5. Over here, another triangle, width of 2, height negative 5. So I suppose that would be the area, you know, -5 if we were counting it, but it's the absolute value, so it's going to be +5, so 10, 12 and a half. Okay, and then the position of the object at time t equals 8. Okay, well, that would be, I could look at it as I start at 3 at time t equals 4. And then I'm going to go to the right by 7.5. And then I'm going to go to the left by 5. And of course, you know, like on a quiz, that'd be a safe place to stop. But on homework, I think we should probably, you know, try to simplify that. And that would be 2.5. Now, let's make the average velocity of the object using a right Riemann sum. Okay, so the average velocity would be the average value of the velocity. So we need to use an average value. I didn't really say when, but I guess I gotta assume it's over the time interval 2 to 9, or 0 to 9. So 1 over 9 minus 0 times the integral from 0 to 9 of velocity. That would be the average value of velocity. If we wanted average speed, that would be where we would do 1 over 9 minus 0 times the interval from 0 to 9 of the absolute value of velocity, because that's what speed is. Okay, average velocity, okay, would be 1/9 of, okay, the first one, a right Riemann sum, 0 to 2 is a width of 2. I would get my height from the right edge of the subinterval, that's 10. Plus 2 to 5 is a width of 3. Right edge would be 8. Plus 5 to 9 is another 4. 4 there. Okay, so 20, 44, and 16 would be 60 divided by 9. I think that's 20/3. Yes, it definitely is. All right, so this next one allows the use of a calculator. Okay, so we're going to need to get a Desmos window going, because in this class, we're using Desmos for the calculator problems, because that's what we can use on the AP exam, and it's definitely the best option for us in terms of like intuitiveness and speed and everything, provided we know what we're doing. But in order to get that confidence in Desmos, especially if you've used a handheld graphing calculator in the past, you need to just practice it, and the homework is really the best time to do it. Okay, so I'm going to get the window going. What we're going to want to do is just type in the velocity equation that we're given. Okay, so we've got v of t equals 1 minus arctangent of e to the t. Okay, must not be, yeah, no, v of t equals 1 minus arctan, and if you type it like that, it knows what you mean, e to the t. Okay, and so it'll graph it for us, and that's great. At time t equals 0, the particle is at y equals -1. Okay, the only thing you can't type in exactly as you're given is a function where the dependent variable is x or y. When that's the case, you have to use a capital X or a capital Y for the name of the function. And hopefully that'll happen to us at some point here in this video, but if not, I'm sure I will force the issue somewhere in class while in practice problems. Okay, so the first question is find the acceleration of the particle at time t equals 2. Okay, so that means we want the derivative of velocity and plug in 2. Okay, so that's going to be -0.133. Okay, that is something we're going to go over here and say, okay, what you can say, okay, we're finding acceleration at time 2, but what you have to do is you have to say how you found it using the calculator. And it seems simple, but like we do just need to write v prime of 2 because that's what we typed in, and that's -0.133. Okay, is the speed of the particle increasing or decreasing at time t equals 2? Well, I know that the acceleration at time 2 is less than 0, but I need to check the sign of the velocity to know for sure, because if they were both negative, which they are, then the speed would be increasing, right? Because they have the same sign. What I was going to say is we're going to need to say that the velocity is negative, but we need to also report the value that we plugged into the calculator and found. So that's going to be -0.436, which is less than 0. Okay, so the speed is increasing because v of 2, and you could say a of 2 or v prime of 2 because we've already equated them earlier, I would be saying v prime of 2 have the same sign. Now find the position of the particle at time t equals 2. Is the particle moving toward the origin or away from the origin at time t equals 2? All right, so if I integrate the velocity, I can find the change in position, and I was given an initial position. Yeah, so that's going to be, I've got y of 0 equals negative 1. Okay, and if I integrate velocity from 0 to 2, that would give me antiderivative of velocity as position, difference in two positions, right? That's the fundamental theorem. So I'd plug in 2 and 0, but I happen to already know y of 0, so that would be equal to y of 2 minus negative 1. Okay, and then I can go and I can actually compute that integral and go over here and say, okay, well, we're going to pull up the integral down here by, I mean, you can go to the keyboard and look at functions, but you can also just type in int. The integral from 0 to 2 of velocity with respect to time is negative 0.361. Okay, so that's going to be y of 2 plus 1. And I could say that y of 2 is equal to negative 1 plus that integral. And that was, so I guess I'm adding a negative 1, that's like minus 1 out here, negative 1.361. Okay. And the average speed of the particle, okay, so speed is the absolute value of velocity, and then the average speed on the time interval 0 to 2 would be 1 over 2 minus 0, the average value of the speed, absolute value of velocity with respect to time. And okay, we can probably just, and then we're going to divide this by 2 and get 0.227. Okay. The next one, we've got a different velocity equation, but it's going to be, otherwise kind of similar. So I get rid of that, swap out the velocity for negative of t plus 1 sine of t squared divided by 2. Okay, there's a lot going on with this graph. Okay, so at time t equals 0, the particle's position x equals 1, so it's going to be very similar. Okay, is the particle speeding up or slowing down at time t equals 2? So we'll need the velocity at 2, and then the acceleration at 2. So I'm going to call for v of 2. That's negative 2.728. And the derivative of the velocity at time 2 is 1.588, which is greater than 0. So I would say slowing down due to the fact that velocity at 2 and acceleration at 2 have opposite sign. Finding times in the open interval 0 to 3 when the particle changes direction. Okay, so yeah, I'm definitely going to restrict this to 0 less than t less than 3. That will give me a lot better idea what's going on. Okay, they said 0 is less than t. Okay, so I'm not going to worry about that. It's going to be, that's the time. So 2.507. Okay, and we're going to need to give a reason for it. Velocity changes sign at t equals 2507. And then the total distance traveled by the object from 0 to 3 is going to be an integral from 0 to 3 of the speed, or the absolute value of velocity. And we need to report the integral that we ran through the calculator. And that's going to be equal to 4.334. Next one has no calculator. All right, it's giving me velocity and acceleration in a table, and using appropriate units, explain the meaning of, 30 to 60 of absolute value of velocity. Well, we know that's going to be, right, so the integral from 30 to 60 of the absolute value of velocity. As to what it represents, the total distance traveled by the object, they said meters, what is the object? Car. And how far would that be? Feet. That would be how far a distance would be if the velocity is feet per second and the acceleration was feet per second per second. Okay, so we've got the meaning, the units, and so we need a time element as well. So between time t equals 30 and t equals 60 seconds. It's unfortunate. Can't fit that on one line, but that's just how that goes. Okay, I'm not sure if I was even writing on the screen and what was visible. Okay, there you go. Approximate it using a trapezoidal approximation with the 3 subintervals determined by the table. So I was going to say, that looks like a lot more than 3 subintervals, but that's the thing that'll happen, right? That they will only be interested in kind of like a subset of the table. Okay, so from 30 to 60, yeah, there is going to be 3 subintervals. Okay, so that would be approximately equal to the width 30 to 35 multiplied by, we're going to average the absolute values of the velocity, so that would be 14 and 10. And we are, getting rid of the negatives because that's, the absolute value of the velocity that we're integrating right there. Okay, from 35 to 50, that's a width of 15, and we're going to average negative 10 and zeros absolute values. And then the last subinterval, 50 to 60, is a width of 10, and we're going to average 0 and 10. Okay, and we don't really need to do the arithmetic on that. There's not really any benefit to doing that. So using appropriate units, explain the meaning of the integral from 0 to 30 of acceleration in terms of the car's motion. Okay, well, we know that this is equal to antiderivative of acceleration is velocity from t equals 0 to t equals 30. So that's v of 30 minus v of 0. So it's how much the velocity changed. So I would say that it represents the net change in velocity the net change in the velocity of the car in feet per second, because that's how much a velocity would change by, from time t equals 0 to t equals 30 seconds. Okay, we do have the values, okay, in the table. Velocity at 30 was negative 14, minus velocity at 0 was negative 20, so that would be 6. All right, so the velocity of the car increased by 6 feet per second from time t equals 0 to time t equals 30. Yes, that's true. It went from negative 20 to negative 14. Right, for time 0 to 60, must there be a time when velocity was negative 5? Let's go back and look at the table and see what we're seeing. Yeah, we went from negative 10 to 0, and I mean, it's velocity. It's got to be moving continuously, I think. Yeah, it even said they are continuous functions. Okay, so I can see that because velocity went from negative 10 to 0, so that would be, I would say, so velocity of 35 was equal to negative 10, which is less than negative 5. And then later, velocity at 50 was equal to 0, which is greater than negative 5. And velocity is continuous. Okay, that's going to give me a yes. There must be a time when velocity is negative 5, because it went continuously from negative 10 to 0. Okay, must there be a time when acceleration is 0? Okay, well, we don't see it necessarily from like a sign change in the table. Okay, if we wanted to apply the mean value theorem from time t equals 1 or t equals 0 to t equals 30, where the accelerations were both 1, we would need to be able to say that the acceleration was differentiable over the open interval 0 to 30 and continuous over the closed interval 0 to 30. And we know the continuity, but I do not see anything about the differentiability of acceleration, and nor am I an expert enough physicist to know if that's a reasonable assumption or not. So I am going to say no, actually. That's I can't say for certain that acceleration is differentiable on the open interval 0 to 60. Yeah, and I don't see a sign change either. Okay, with the continuity, if I knew there was a sign change, I could say there was definitely a time when the acceleration was 0, but I don't know that. So yeah, that's maybe the first time we've had a no on a mean value theorem problem, and it's probably gonna be the only time the whole year. It's very uncommon. Usually we just apply the mean value theorem and it works. Okay, so the particle moves along the x-axis, so its velocity is given by a differentiable function. Okay, I can see that the velocity is 0 at 0, 3, and 5. And the acceleration is 0 at t equals 1 and t equals 4. Okay, that's believable. The areas are 8, 3, and 2. Oh, okay, 5 to 6. Maybe I could sketch on that a little bit. Okay, so from 5 to 6, they're talking about that business right there. So I'm going to say 8, 3, and 2. Okay, so that's what they've given me. On the interval 2 to 3, is the speed of the particle increasing or decreasing? Okay, let's say, all right, we're looking really through here on the time interval 2 to 3. Velocity is negative and getting closer to 0. So I would say it is slowing down. The speed is decreasing. Okay, but I think about justifying my answer, I'm going to say speed is decreasing, clearly answer the question and explain why. Because on 2 to 3, velocity is less than 0 and is increasing, so I can see has a positive slope, and okay, which would give v prime of t is greater than 0 on the time interval 2 to 3. I'm trying to think of, we could also say, alternatively, visually, we can tell that the absolute value of v of t is decreasing, which is really all the same thing. Okay, what is the position of the particle at time t equals 5? All right, so the integral from 0 to 5, yeah, they gave me the position at time 0. So x of 0 equals -2. The integral from 0 to 5 of velocity will give me the difference in positions. And I know x of 0 was -2. So that's x of 5 plus 2. Okay, and I can, compute that integral right here by adding areas, right? It'd be -8 plus 3. So -8 plus 3 is equaling x of 5 plus 2, and so I can just solve for x of 5 by subtracting 2 from both sides. So that'll be -8 minus 2 more plus 3. I think that's going to be -7. And the total distance traveled by the particle on the time interval 0 to 6, okay, and I would just need to give, the integral from 0 to 6 of the absolute value of velocity with respect to time is going to be 8 plus 3 plus 2. And that's going to be 13. All right, and that's going to be all for this problem set. I've got another set of more recent AP Calculus free response questions, a lot with the calculator, but I'm going to record those in a separate video. So that's going to be all for this one. Thanks for watching.